Okay, dear colleagues, we are starting with our next session. It will be given by Hengtong Zhang. He is from Harbin Institute of Technology, a professor here, and he will be able to tell about poisoning, cynics poisoning data, and how to deal with it, especially in some applied machine learning models. This talk is based on his publications and top conferences like EDD and many others. So please welcome our speaker.
Thank you. Okay. Okay. Thank you for the introduction. And okay, you can see the PPT right here. For today, my topic is called the assessing the vulnerability of applied machine learning models. Also, maybe you have just taken some other lectures. It's about the good things of the machine learning models, such as the machine learning models can help us do something like the self-driving, the large language model, and something like the very basic tasks like face recognition, right? But today I will talk about something like the ugly or the bad things about the machine learning models. It's called the vulnerability of machine learning models. And what this domain really focuses on is try to find the ways that we can destroy or make the machine learning bias based on the adversarial test samples or the training samples. And firstly, let's see this. The application of machine learning models, as we can see, is various. And I do not need to make some other descriptions about this one because everybody know that it has been used in almost all the fields. But there's a thing called, can we really trust the machine learning models? And these are three examples. For the first example, it's about the stop sign in the United States. And when the drivers see the stop sign, and when a driver sees the stop sign, it will pause its car and wait for the pedestrians to get past. And when we have the autonomous driving systems, and the car itself have to recognize such a sign and stop, and then wait for the pedestrians to get across. But at about 2015, some of the early researchers, such as in Goodfellow, who is the author of the GAN, the Generative Adversarial Network, they found that such kind of traffic sign can be easily perturbed if we get some patches. Some patches means the black one or the white one. Some patches, some unrecognizable patches on this traffic sign, in order to make the autonomous driving system cannot really recognize whether it is a stop sign, and it becomes a substantial threat to the security of such a driving system, because because for the pedestrians, they are expected to see the car themselves stop, right? But the car it does not stop, and it causes a potential threat. And the second thing, and the second example is glasses to fool the face recognition. It is it is a kind of attack that is more elegant than the first one. The first one, you have to make some ugly patches, but the second one only needs a very specific person to to, wear very specific glasses, and they use the texture on the glasses in order to influence the recognition system, the face recognition system, in order to make them unable to identify who has get access into the room. And the third one is about the attack on the LiDAR-based autonomous driving. It's about attacking the signal system of the autonomous driving. As we all know, the autonomous driving system may need some may need the MM wave or the LiDAR signal in order to know what happens around. But if we can have a adversarial attack on such a LiDAR-based system, it will also cause some security threats, especially when they are driving on the highways. So these presents the substantial threat against the machine learning models. And so there becomes a brand new field called the adversarial learning. It is a research field to investigate whether we can trust machine learning models. And today I will present a series of such a threat. It is called the data poisoning attack. What is a data poisoning attack? You can just see such a diagram in order to know the entire workflow. For the above, you can see that the traditional machine learning workflow is like this. You have the training data, you get the model trained, and there's a test data, and there are some test data, and get into the benign model and make the final prediction. But when the training set is poisoned, just as the things happened at the bottom, you can see that some poisoned data are injected into the training set, and after the model training, after the training, the model becomes biased and poisoned. Once there are some same test samples get into the model, it will have it will have the falsified prediction, and the predictions themselves are modified or influenced. So this is called the data poisoning attack. I do want to make it a systematic lecture about how to do the data poisoning attack and how to defend them. But I think it is the nature of computer security or the AI security. The vulnerability of these models just happens point by point, which means that you have to dig out, which means that you have to look into some very specific features or some very specific properties of such a model in order to build a very smart, a very elegant, or a very practical attack method. So today I will share 3 of my papers that I published in the recent years in order to let you know how does this data poisoning attack take place. And these 3 papers just represent 3 kind of representative technical path of to carry out the data poisoning attack. And at the end of this lecture, I will also talk a little about the defense and the future directions. And this is the overview of this talk. First, let me talk about the first one that is published on KDD 2021. It is called the data poisoning attack against the outcome interpretations. Let's get started. The machine learning models requires interpretations, especially when it comes to the life critical applications, such as the object detection in the autonomous driving system or the diagnose system when we are trying to assist the doctors or physicians doing the medical diagnose. And we do need the interpretation because we have to know how the model makes its decision in order to treat it as a black box model. Because if it is it is just a black box model, we cannot really find the vulnerability of the model beforehand. So we need the interpretation. And this is a diagram describing how the outcome interpretation take place. And as we can see, there's a dog right here in the image, and a classifier want to tell us whether there's really a dog in the image, and just this input sample pass through the machine learning models and get the prediction results, and the medium layer of these parameters just get out by the interpreter and compute for the final interpretation results. And this is a threat model of this. For the AI security domain, every single context, we need a threat model in order to tell us what is the attack goal and how the attackers can carry out such an attack and the knowledge of the attacker. So the threat model here is that the attack goal is to manipulate the specific target samples, interpretation results with their classification results and change. Here I want to emphasize that the classification results have to be unchanged because otherwise the users will not trust the model anymore. They will not use that. So the manipulated interpretation cannot be delivered to the end user. And the approach is that the attackers can add the poisoning samples by injecting or modify the training set. And the knowledge of the attacker is that the attacker knows that exactly the architecture and the parameters of the target interpreter and the corresponding machine learning model. And for the interpretation approaches, I will also have two representative one here. The first is called the backpropagate guided interpreter. It is calculated by taking the gradient from the prediction results FCX here regarding with respect to the input X. It is a very well known interpretation method in the early stage. And the second one is also called CAM. It is called the class activation mapping. This is quite widely used in the computer vision papers. Some of the modern ones is called the grad CAM, and it is calculating like this. Firstly, calculate the attribute map, and secondly, calculate the CAM interpretation using the second expression. And here how to how to carry out such an attack. We have to have an intuition. We have to have an intuition. The intuition is just like this. I will write it on the whiteboard. The intuition is like you have two cluster of samples, such as here, here, and here. They may have some kind of overlaps, and they are classified by this kind of boundary. And if you want to change or modify the interpretation of a single sample like this, a very straightforward strategy is like you put some you inject some kind of the poisoning samples right here, here, and here in the feature space in order to drag the interpretation of this one into the place that the attacker desires. And this is quite the intuition because these samples have a very strong influence on this sample, right? And through this encirclement, you can just make the attack happen. And the formulation is like this. We formulate it as a bio-level optimization problem, and I will try to explain this to you also on this whiteboard. And as we can see here, there's a minimize about the first term. The first term is about the GC minus the G. This is called this is to make the interpretation of the target sample just as it desires, which means that this is which means that this is the interpretation that desired by the attacker, which means that we want to reshape the interpretation into this thing, and this one is the original interpretation, right? We want to make them as close as possible, but at the same time we have to consider the encirclement, right? Otherwise the injected samples cannot project their influence on their on the target sample. So we have the second term right here, which is p minus t. Right? So this thing makes all the poisoning samples close to the target sample. And for the third thing is called the and for the third thing is right here. This means that the target sample have to be remained as the as classified as C after the parameters are changed by the poisoning attack, because we know that the model will be retrained on the poisoned data. So the CT right here is not it is not a benign model. We have to make the target sample making the same decision compared with the original benign sample. And the condition here, subject to beta is okay. I use Z here to represent the sample itself and the label, right? To make it simple. So this means that we have to retrain the model on the poisoned data set. The poisoned data set is just right here. This injected to the original clean data set, and then make the attack happen. So that's how we formulate it into a bi-level optimization problem. And by solving it, we can get the poison sample and inject it into the training set. Any questions? Okay, go ahead. Okay, I will get close to you in order to.
Yeah, thank you very much. Could you please clarify about steps, how the data is becoming poisoned and how we get the P sample? Am I right that first the model is trained on the union of ordinary data and poison data, and it does not depend on the attacker, and the attacker just finds the P, a one sample which is close to target but fakes it.
You find you asking how to find the samples that I should modify on in order to take in place attack. This is the case?
No. I'm just asking at which place attacker is doing something.
Oh, okay. Thank you. I will answer this question. At the training phase, as I said in the threat model, the attacker can get access to the training set, right? And they can find some samples that are close to this one in order to modify these samples and make the poison sample here. This is one kind of strategy. Modify on the original sample, or otherwise you can just introduce some other samples in order to encircle the target sample and make modification on these newly brained samples in order to make this attack happen. And this learning objective is only for how to solve for the ideal poisoning modifications in order to have it encircle and have the specific influence. Okay, yeah. Any other questions? Because it is something about the math and okay. If no further question, I will continue and may leave the and you may ask by the end of this lecture, right? And having this having the bilateral optimization problem right here is intuitive, but solving it also have some very practical challenges, and I just present here. I will be here, and you can see that there's a learning algorithm. We have several challenges. And I think the very substantial challenge is that after the poisoning, the end user have to retrain the model. How do we guarantee that the poisoning samples we injected can also be used during the retraining? Because the retraining, we have the random initialization, we have the random training trajectory, and we have the running and we have the random optimization path. How do we make sure that our poisoning samples can be compatible to these training trajectories? Let me give you an example. This is something like the this is something like the nonlinear functions, and for the machine learning, you may have to use a strategy to here, and then get to the optimal theta, right? But if we have another training strategy, or we have another training trajectory, we cannot make sure that the poisoning sample that designed for this path can be used also for this path, right? And this become a practical obstacle when we are doing this one. And in order to get across this, we have several strategies. For example, at right the bottom of this one, we have the ensemble the updates of K models. Because after K models, we will diminish such kind of we will diminish such a kind of randomness caused by different learning path or the learning trajectories. And also, we find that since we have something like something like this, right? And the formulation of the interpretation itself has something like the have some nonlinear things, or even the discrete things, non-continuous things. So the learning, itself may facing the parameter update fluctuation. So we have the look forward strategy in order to let the model look forward into the next batch when we are designing such a sample, and then we will make the update step more smooth, and it is right here, took a forward of a single step. And finally, we use the first order approximation, because after all, we have to make the design efficient. And the first order approximation using the Taylor series, from my perspective, is enough for this one, because we are not pursuing the quantity of the vision quantity of such kind of a poisoning sample. We are looking into the whether such a poisoning sample can be effectively used to get the model poison. So we're not focusing on the quantity of the image using some art like the DDPM. We are not quite interested in that. We just use the first order approximation. We did our experiments on the Stanford dog data set to tell the difference between the dog and the cat. And the victim classifier is called the ReasonNet 13, and the two-layer deep neural network for multivariate data. And we have the victim interpreter, as I described before, it's called the GRAD and the CAM. And the baseline that we have is called the watermark, because at that time the poison attack is still at its early stage, and there's there's very few poison attack methods can get across can get across the difficulties such as this different learning trajectories or something like that. So I just use the watermarking as the baseline method. And let me just see some interesting results right here. You can see the case study right here. We have a cat and dog, and for the benign model, the interpretation results just focus on the head of the dog, because this is This is the very part that we can tell whether it is a dog or a cat, right? But through our manipulation, we can see that um, the heat map just detour from the face of the dog and run into to the body of the dog and to the other places, which means that we have make the interpretation inaccurate. And also regarding the grad interpretation, it becomes totally different. Originally, it focused on the body of the dog, but after the attack, you can see that the interpretation heat map just just get everywhere. For example, on the door of the wardrobe or on the floor. So this means that our model can really can really destroy the performance of such kind of interpretation method. And also for the convergence, we can see that for the both upper level loss and the lower level loss, they have a very good very good convergence property, and which means that our learning strategy can successfully solve this 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 difficult level optimization problem in a very smooth way, and the parameter after this one after using this one get a really good convergence property. And for the second one, I will I will head into the I will head into the research paper that I published on the IGCI 2019. It is called the data poisoning attacks against the knowledge graph embedding. And as we see, for the first one, we focus on the data structure. What we focus on is the data structure image, right? And for the second one, we focus on poisoning the knowledge graph. It is kind of heterogeneous network, and it become discrete, and so the attack strategy should be different. What's your problem? What's your question?
A question about previous slides. Am I right that the attack, first we have some trained model, not by ourselves, but by other people, which are working in production. And we are trying to train the similar model with poisoned samples. And by you, for algorithms, get another poisoning samples from the production model. So
okay.
So we try to mine the poisoning samples using our copy of the model, but we do not access to the weights of the original model, which are in production.
Oh yeah, that's correct. That's correct. We for this one how to say that? Okay, for this one, let me answer like this. You for this executive paper, you do not need to make the parameter identical to the one that held by the end user. The end user themselves can retrain the model by themselves, because otherwise the thread model or the context is or we can say the setting is not practical. Which the only thing that we have the only thing that we need to get online is that I have ResNet 18 and you have ResNet 18, and I just make the model and I just make the pointing samples according to the model from my side. You can also retrain the model on your side, and this as long as they are all ResNet 18 according to the setting of the paper. But we have to say that the pointing samples themselves have some transferability. For example, I use the ResNet 18. You have ResNet 50. Some very similar result will also happen. But I didn't take such kind of experiment. I cannot say I cannot say by which degree. But such kind of transferability do exist for the poisoning samples.
Yeah, thank you very much.
And this is called the knowledge graph. I will continue. I will continue this one. The knowledge graph is an organization of entities and the relations as a direct heterogeneous network. For example, there's a singer here. It's called John Lennon, and Yoko Ono is his wife, and he is a husband of the Yoko, and he born in Liverpool and located in the United Kingdom, right? And this is just like this is just like a graph that organizes all these entities, all these concepts, and all these relations together. And and all these relations we can also regard it some as facts. For example, John Lennon born in Europe, and these are the facts. And what is knowledge graph embedding? It's a knowledge graph embedding is kind of representative. Is a kind of representation learning method that learns to represent these entities in the continuous vector space in order to make them computable. Because the modern machine learning system, especially the deep learning system, they have to get the vector representation, continuous vector representations as inputs or as the main layers in order to make them happen. And this is and the trans E right here is and the trans E right here is a kind of it's a kind of the knowledge graph embedding method, and it is just computed like this, which means that the representation of the entity E here of the head entity and the tail entity can be well harmonized by this relationship entity. And by this relationship representation, and by minimizing such a function throughout all these facts in the training set, we can get the learned representation of the head entity, the tail entity, and their representation and their relation representation. And key and knowledge graph embedding enables easy computation and inference on these graphs. For example, it can be used to answer the question like, what is the relationship between the John Lennon and the United Kingdom? And and the only thing you need to do is to use the functions that I introduced in the previous slides in order to find the very in order to find the very plausible or we can see the very reasonable relation between the head entity and the tail entity, such as the born in, located in, or play for. And the answer here is that it's born in. This is the most reasonable result. And for the downstream applications, they can just make decisions according to such kind of question answering decisions. And there's a vulnerability issue right here. Is it possible to significantly influence the soundness of a fact or soundness of such a kind of a prediction, such a kind of a question answering by manipulating the representation E, R, or here? Right model here is that we want to degrade the soundness of target fact samples measured by the fact soundness scoring function f, and the f is it's just like it's just as we formulate in the previous slides. And the attacker's approach is that attacker can add or delete some well-picked facts in the knowledge graph, and the attacker's capability is that they can access the entire knowledge graph. But according to our experiment, if as long as they can get access to the part of the knowledge graph, the attack can be carried out successfully. And and the highlight of the paper is that at that time, no previous work can work for the heterogeneous graph due to the complexity nature of the bi-level optimization formulation. Because if we also formulate this problem as a bi-level optimization problem, you can see that it introduced something like the tensor computation, which is over complex for our task. And especially for the case that the knowledge graph themselves are large in scale. So we have to bring a very efficient one. We have two strategies. First is called the direct attack, and the second thing is called the indirect attack. The direct attack is that we just modify the neighbor of the target effect by adding some new edges to the tail entity or to the tail entity or to the head entity. And the indirect attack means that we have influence path. We have an influence path. We add the new entities or delete the existing entities right on the entities on this path in order to propagate such a kind of influence to the target effects. I will also use the whiteboard in order to describe how this attack happens. Let's suppose there's a fact that we want to influence, right? We want to add some new facts right here. And how do we determine which kind of which new fact we should add? It is like this. We want to modify the interpretation of this head entity into a modified one like this. And this one should be like we just take a gradient by a single step in order to make it an ideal shifting direction, and it is like this. The second thing, and after we determine that this is the optimal or this is the desired shift on this head entity. The second thing is that we have to determine the fact that we need to add or delete in order to make this shift happen. and then we just have the direct attack and direct deleting attack or direct adding attack. And since time is limited here, I will only describe how this what are these two terms mean. The first term means that we have to modify. We have to find the we have to delete the facts that contributes to the soundness of the current embedding and contribute to the shift of the embedding as desired, which means that we destroy the existing embedding and then we build the desired embedding right here. And for the direct adding attack, we have right here. We heard the soundness of the current embedding, and we also have the have to make the shift contribute to the desired representation right here. And for the indirect attack, we have to we have to do it recursively, which means that we have to first determine the desired. We have to firstly determine the desired representation shift of the original fact of the target effect, and then determine the desired shift on every single entities through such a kind of path. And after we have a solid idea of how the representation of the entities on this path should be changed, we can add this. We can use the exact same strategy in the direct attack in order to determine which fact should be deleted and which fact should be added. And also we have to choose a path in order to propagate such kind of influence into the target fact. Because if the path is not chosen properly, the propagation influence will be very weak, and the attack will not be carried out efficiently. And let's see some of the experiment. We just take the experiment on the FB15 and the WN18 dataset, and using some notable target KGE method such as trans-E, trans-R, and RICO. And we use the MRR hit top 10 as the attack metric. And the smaller these metric are, the better the attack performance is. And we can see overall, the result is work very well, especially for the RICO embedding method on the WN18 dataset. And we have a very worrying finding is that for the direct adding attack and direct deleting attack, we only need to add or delete at most about 2 facts in order to make the embedding of the target sample of the target fact detour significantly. So this marks are very substantial, a very significant threat, because if we have a defense model, we want to just defend such kind of a one fact injection. We have to get through all the samples by at least a single time. So it causes a very large overhead, and it can also be called something like the resource exhausting attack, which means that we will make the learning system very inefficient if such a potential attack exists. And for the final one, I will talk about my my research paper on the on poisoning the next item recommendation. It is published on www 2020, and the journal version is published on the TKDE 2023. And I also have some other research papers regarding the attack on the recommendation system, and I will only present this one today. The next item recommendation is a sequential recommendation system, and will predict the next item that user will choose based on his or her behavior history. And the attack model here is that we want to promote a set of samples to as many users as possible, which means that we want to place all these recommendation results into the recommendation list of these users in order to have them choose these target models as more as possible. And the attack approach here is that we can inject the controlled users through the to the recommendation system, and they will carry out the visit or the rate behavior step according to the guidance. The guidance is proposed by the attack model step by step. And for the attacker, they can access the full history, and but they cannot know the target model. It is called the black box attack, and they can only have a limited number of feedbacks. Here the major challenge come from the limited feedback, which means that if we inject a batch of poisoning sample to poison a black box model, we are expected to see how the model really behaves after such a single batch. But nearly every online commercial system have a rating limit, right, for each user. So it is impossible for us to do it like this. So the strategy that we propose a local surrogate model or a local proxy model in order to simulate the behavior of the target recommendation system to carry out such a kind of attack. and the proposed method and the proposed framework is right here. As we can see, we are going to attack a system on the remote. It is a black box recommender, and we have and we have a recommendation simulator right here in order to simulate the behavior of the target black box model. And we also have a reinforcement learning based behavior generator in order to generate the user behaviors. Because the user behaviors themselves are are some kind of multi-step decision problem, which is identical to the setting of the reinforcement learning. And I want to inference and I want to inference is here. It is called the outcome estimator. Why do we need such a kind of module? Because even on the local side, if we have generated some initial pointing samples, we inject them into the recommender simulator and get the feedback. The time cost of such kind of retraining of the recommendation simulator is still too high, and it is still and we can still and it is still impossible for us to finish the design of this kind of pointing samples within the reasonable time. So we have to have a way in order to approximate the influence of these poisoning samples on the model parameters in order to make it a reward or a feedback to the recommendation to the reinforcement learning based generator right here. So so these are the things here why we need a simulator, because we cannot get enough feedback from the target recommendation system, and why we need an outcome simulator, because we need feedback to update the reinforcement learning policy function, and conventionally we have to retrain the target model to get the feedback, and it is very time costing, and how we do the outcome estimation. We just derive the approximate of the influence of. We just we just derive the approximate influence of the poisoning sample on the model parameters using the robust statistic results right here. This is a mathematical tool called the influence function, which is proposed by a very classic statistic literature. And in a nutshell, it just tells us how an injected sample will influence the parameter right here. And the main result is that the change on the parameter can be approximated by the inverse of the Hessian matrix times the gradient of the loss with respect to the parameter. And you can see that we it also brings quite a quite complex issue here, because we have to compute the Hessian vector, the inverse of the Hessian vector of the Hessian matrix. But there's a conclusion that this one can be approximated by the Hessian vector product. And also if we have an approximation of how the parameter changed after injecting this kind of sample, we can use the chain rule in the calculus that we learned at the during our undergraduate, in order to estimate the influence of the poisoning samples on the recommendation score of the targeted items to our target user, apart from the change of the auto parameter. This is quite straightforward because as it is a recommendation system, the score change is largely influenced by the parameter change, right? So we can just use a change rule in order to derive such kind of thing. And we can see here, it is called the Hessian vector product. And we have a very, we can avoid directly compute the inverse of the Hessian matrix. And we have very mature tools or compute such kind of mathematical expressions. It is called the Hessian vector product. We have a mature computation tool for Hessian vector product. This is experiment. I will go through really quick. And the target recommendation and the victim recommendation models are the EPRMF, MPMC, FPMC, trace recommendation system, and the GRU for REC. And the baseline threat at that time is called the cohabitation attack, which fix the cohabitation between the users and some between the target user and the target items in order to make the attack happen. And the metric here is called the display rate, which means that the fraction of the target users whose topical recommendation results have the target item. And this is attack effectiveness. As we can see that compared with the baseline methods, our methods compared with the existing attack methods, our attack methods just have just enjoys more display rate. It is called the Locky method. And also this is a attack. This is attack effectiveness with respect to the number of steps. The number of steps means that how many user behaviors a user have to a control user have to do in order to make the attack happen. This one is called the attack effectiveness with respect to the control the number of control users. We can see that if we have only about 1 to 3% of the users are controlled, we can launch a very successful attack and brings up the selling revenue of very specific items. And this is the summary of my research contribution in this field. As we can see, the representation work just covers the attack against the non-lithographic embedding, the attack against the recommendation system, the attack against the model interpretation, the attack against the machine learning fairness, and also the probable and certified defense for the single-to-six model. This is something like the theory paper. And for the future direction, future direction is that the vulnerability analysis of these kind of applications are still on their early stage, especially for the healthcare models due to their inaccessible of the learning data, and for the mobile sensing due to their physical properties, because the mobile sensing system have a very unique characteristics. And for the NLP models, for the large language models, we also have to study their vulnerability, but the technique should be different, because all the methods that I talk about today cannot meet the huge scale of the current large language model, because the parameter set is it's really so huge. And and also we need some and we also need some theoretical approaches. The theoretical approaches, unfortunately, is still missing right here. Let me talk a little bit about the status of the defense. Although we have some kind of the attack approaches, the defense is still missing right here. And there are some intuitions. For example, this is the benign data distribution, and a very straightforward way to get to defend the model against the pointing samples is to find the outlier, because some kind of the early attack methods, it will cause the outliers of the data distribution. So this is a way to find that. And another thing is and another intuition is like finding the densest part of this model, because if the model is collected naturally, the density should the samples should not be focused on a very narrow region of the data distribution. So such a kind of dense part is it may be the place that poisoning samples may locate, and this is something like the second intuition. These two kind of intuition are all about the anomaly of the data distribution. And there are also some some kind of method. It's called the partition and aggregate. It means that if we have the poisoning sample right here, we at least have some other places that are not infected, are not contaminated by the poisoning sample. So we have to, so we can use these, benign parts to train several separate models, and use the majority voting to get the correct decision, which means that we have several models such as theta 1, theta 2, theta 3, theta 4. So this is poison like this. We can also use these things in order to get a majority voting for the correct answer, right? And the researchers from the I should say from the Maryland University, right? If I remember correctly, just propose a theoretical guarantee by using this kind of majority voting strategy, which means that it has some theoretical results to tell us how robust a model is if we partition them into several parts. And there are also some empirical methods such as adversarial training, but adversarial training itself is also time costing, not so efficient. So the theoretical part and the defense of the model against these kind of poisoning attack is still an open question and require researchers to work on. And this is so much for my lecture today. Thank you. And feel free to ask me questions. Thank you. You can just say it without speaker, and I will just here right here.
Okay, so my question is pretty simple would be, so we have like a problem to poison a sample of data, and how many examples do we need to poison a model? What is like?
If you say about it empirically, we empirically for these kind of papers, they are separate. For the attack against the recommendation system, we may need about 1% or 2%, lower than 3%, in order to make them happen. And for the poisoning against the non-graph embedding, we only need about 1 or 2 samples. One or two samples, not 1 or 2 percentage, right? Not 1 or 2%. 1 or 2 samples in order to poison a single fact to make the potential prediction on that kind of fact fail. 1 or 2 samples. And if we do the indirect attack, we may need about we may need 10 or 20 samples because we have to propagate such kind of influence. But even though it is about 10 or 20, it is along all the approximate on the propagate path. So it is quite so it is not quite focused. It is still difficult for the defender to tell which is a point sample.
Okay, thank you. And another question regarding your first paper. You mentioned that you apply some gradient-based procedure to generate poisoned examples. Is it correct?
Mm.
And so, can we adopt this approach to work in NLP setting?
Yeah. For the I didn't do quite much research on the NLP setting, but there are some but there are some existing work on the NLP setting, and I will state some gist of these models. The for the poisoning attack or the adversarial attack against the NLP models, the most straightforward way is called the word substitution. The word substitution means that we substitute single words or some phrases or some expressions in a sentence in order to modify the conditional distribution of some kind of prediction. Because we know that the language model is all about the conditional distribution, right? The language model is about conditional distribution. Because, because we have to predict the next token according to the previous history. Yeah. We can use we can use the word substitution to fake some kind of a non-natural conditional probability in order to influence the large language model or the language model. And it is like just like injecting a backdoor into the model. And when such kind of conditional when a specific condition happens or triggered, the distribution that we designed will expose and cause some kind of the and cause some destroy to the performance and to the efficiency of the model. And that's how the that's how the attack on the NLP model works. There are also some since today is the era of generative model era. It also has some kind of the attack approaches directly using the generative model to get these poisoning samples instead of just purely doing the word substitution. So this is so these are the two paths that may use to get poison.
Okay.
Sample.
Okay. Thank you.
Yeah, thank you very much for the lecture. I would want to ask one question. Can the uncertainty-aware models can be sustainable to such type of attacks? Have you researched this question, or maybe you know? If the model predicts not only the, for example, label, but also its uncertainty and its certainty in this label. Okay, confidence. Yeah.
Okay. You mean that we are not just focusing on poisoning the final prediction result. We are focusing on poisoning something like the confidence rate or the confidence region, right?
No. My question about just like this. If we in production use not the just simple models which predict labels, but which predict labels as well as its confidence in the label.
Okay.
And in case of your attack, maybe the poisoned sample will give a very bad confidence in the model, and that's why it is easy to detect it and take some actions.
Oh, you mean that the confidence-based method as a defense, right?
Yeah. And maybe used as a defense and other methods which attacks models with confidence.
I think I didn't do quite much research on this one, but I think attack a defense using the confidence region may not be a good choice because just as the example that I proposed on the whiteboard, the the feature of such sample according to the learned model are shifted significantly. So despite you bring some techniques such as the trust region or something like the confidence score in order to justify, it is, I think it just the prediction just purely changed. It is not just like shifting a little bit on the in terms of the confidence. It just purely changed. So I do not think it may have a very satisfactory result. And also I didn't see much research, and I didn't see many research papers doing this kind of things in terms of the confidence. Professor?
Thank you for your lecture. I would like to ask, as far as I understand, the current large language models are trained on really huge corpora. I think that some of the poison data inevitably will be there in these huge corpora they trained on. So how do you think, are there any methods so we can check or somehow know if there are such data and what we can do about this?
I always say that you see that the
Large language models, yeah.
they have their data already poisoned.
Yeah, that's true. Yeah. The question is, can we detect if there are some data and what we can do about this?
Oh, you mean that? Okay, let me repeat your question. What do you mean? What do you mean that it is not about the defense? It's called the detection and the data sanity, right?
Yeah.
Yeah, data sanity just as I placed right here. Data sanity method is a very early stage method, in this field. Particularly, some of the representative works are proposed by the Stanford University at about 2019 or 2018, something like that. But after that, they have diminished because it will cost very much false positive detection results. For example, if we only have a boundary of in order to filter out these samples, we will have many pressure samples. They are benign, but they are excluded from the training set. And this is the major problem why such a kind of method just becomes the number becomes smaller, in the recent papers. But I think in the industrial setting, it also has its room because it's quite efficient. What I say that the certified defense or the adversarial training, they are not quite efficient, especially for the large language models. So I think this matter still have a room, but for the research, it may not get a very state-of-the-art method. It may not get a very state-of-the-art results, especially regarding the false positive rate.
Thank you.
So you here in your presentation, you mentioned many different types of attacks. But do you know any cases when one of these attacks were really applied to some industrial system?
Well,
have you ever read in some newspaper or in some paper? I don't know.
I should say that some of the companies, they may carry out something like called the red flag competitions in their internally, but they may not have them published on the newspaper because it means that they are researching the they are having the research, having the industrial scale research on the attack, and they have for fear that other will suspect them, carrying out such attacks against their competitors. So so many companies they disable, they have taken such kind of research, but for the attacks from the hackers, they have some cases. For example, before the ChatGPT, there's a chatbot that is trained by Microsoft at about 2016. They see that the chatbot itself get poisoned and it become begin to say something like the dirty word or something like the improper sentences, and people say that it is poisoned by the user provided data. So this is kind of a example, and I have write it as a appeasing example in one of my research paper that is published on EMLP 2021. It's called the Profanity Avoiding Defense, and it is just to face with the report that Microsoft chatbot was poisoned at 2016.
Okay, thank you.
Any other questions?
And do you know do you know any good maybe you can recommend some good frameworks for guardrails for LLM? So what's your experience? Guardrails for large language models. Guardrails, which it's a kind of framework using which you can prevent large language model from extracting from inside and from prohibited information or correcting answers of large language model. So standard frameworks, for example, Llama, it has own library for this kind of things, but maybe you can recommend something else. What's your experience on this?
Oh, you mean the large language model censorship methods, right?
Sorry?
Censorship, which means that you have to filter.
Yeah, for filtering or for filtering answers, for filtering requests from users, or for checking the information, this kind of things.
I myself did not carry out much research on this field because the censorship of the large language models themselves, it is a quite a different topic, and because it is not like training a model or defense a model against these kind of poisons or the adversarial samples. It's all about how to remove these kind of inappropriate answers or inappropriate questions, right? So the strategies they are different, and the metrics to evaluate them are also different. And for the censorship system, the major the major goal is not to have these kind it's not to have these results exposed to the end user, right? So it can tolerate high a false positive rate because as long as a user have something input and it has something improperly happen, and it will just stop to expose to the end user. So their strategies are different, and the method, according as far as I know, is also something like the keyword filtering, text classification, or this kind of methods. It's not quite similar to the defense methods that I talk about today.
Okay, thank you.
Okay, any other questions?